Okay, this is section 13.3, second half on curvature, and this is sample question number 6. We're asked to find the curvature for the vector function rt equals t squared, and t. Well, one way to do this, of course, is to rewrite the parameter, to use parameterization, and then to find the curvature through the reparameterized variable. But we're going to see in this case, that's not going to work out. R prime here is not too bad. It's 1, 2t, and 1. So far, so good. The problem comes when we look at the magnitude of R prime of t. And that's going to be 4t squared plus 2 under the radical. Now, if we were to try and integrate this, that is not exactly an easily integratable form. And because of that, we should abandon trying to use arc length and reparameterizing in order to find whatever the kappa value is. There are alternatives for evaluating what the curvature is that don't involve looking at parameterization, and this is a good candidate for it. Mostly because this integrand would make for a really unpleasant integral. So let's not go there. Instead, let's use the definition of curvature, which is that it's the magnitude of r prime crossed with r double prime divided by r prime's magnitude cubed. Because it turns out for this particular vector function, these aren't too hard to find. Okay, we already have r prime. Let's find r double prime so that we can work on the cross product. So r double prime would equal 0, 2, 0. And now that we have r double prime and r prime, we can actually write what would make up the numerator here, which is r prime crossed with r double prime. And that's going to end up being a 3 by 3 matrix, I, negative j, k, and then we put in the first vector r prime, 1, 2, t, 1, and the second vector 0, 2, 0. And this shouldn't be too hard to evaluate. I love seeing those zeros there. Okay, so this cross product is going to produce, the I component is going to be 0 minus 2, so it's negative 2. The j hat component, I got to remember the extra negative is 0 and 0, so it doesn't matter. And the k hat component is going to be 2 minus 0, so 2. So this turns out to be r prime crossed with r double prime. And if I want to find the magnitude of that for this numerator, of course, that's just going to be 4 plus 4, which is 8, and the square root of 8 is 2 radical 2. Now the denominator here is just going to be the magnitude of r prime cubed. So here's r prime. Let's look at its magnitude. We've got its magnitude already. It's right over here. And then what we want to do is we want to cube that. Well, that makes 4t squared plus 2 to the 3 halves. 4t squared plus 2, and the whole thing to the 3 halves. And that's it. That's the curvature function. It may not look very pretty, but if I know t, I can simply plug it in, and that's going to give me the curvature of the function at that point. Again, this is a good example of when we might want to abandon parameterization. If this value for the speed turned out to be an easy integrand, I might still go in that direction. But the minute I check out what the magnitude of r prime is, that's the time to make a decision as to whether you're going to use an alternative definition of curvature. And in this case, boy, we got to the answer a lot faster than if we had tried to integrate that.